Hello, everyone, and thank you for joining us today for the AIEI webinar series on the balanced mix design. We are at the top of the hour, so we will get going while we have some participants all, in the meanwhile joining us. So today, this is session 4 of 5 in our BMD webinar series. We're going to be focusing today on the BMD testing conditions. And our speakers are Tim Aschenbrenner and Derek Niederplant from the FHWA. Before we get going, I'm going to give you some housekeeping items. Please keep your microphone muted during the webinar. If you have any questions, go ahead and post them in the chat box during the webinar, and which you can access by clicking the chat in the meeting controls. Throughout the webinar, I will compile the questions and the presenters will address them at the end of the webinar as time allows. If there's any unanswered questions due to time constraints, we will attempt to respond to them separately. And so everybody would know this webinar is being recorded, and a link to the webinar will be provided at a later time and posted on our website. As a quick recap, our first and second sessions basically cover the BMD implementation plan and validation, while the third session back in April focused on specimen fabrication, where we discussed strategies to reduce variability in BMD testing through consistent and standardized laboratory testing practices and protocols. Links to the recorded webinars are provided here on the web, on the PowerPoint presentation, but I will also post the links in the chat box. Today's webinar is on BMD testing conditions, and we do have one more webinar coming up in June, on June 3rd, on BMD in quality assurance. If you haven't yet registered for the upcoming webinar, I also posted the link for you to register in the webinar in the chat box. Well, before we proceed, I would like to share the following disclaimers. The material is disseminated under the sponsorship of the U.S. Department of Transportation in the interest of information exchange under the cooperative agreement number listed. The U.S. government assumes no liability for the use of the information presented. Except for any statutes or regulations cited, the contents of this presentation do not have the force of law and are not meant to bind the public. This presentation is intended solely to provide information on existing legal requirements and agency policies. The U.S. government does not endorse any products or manufacturers. Any trademarks or manufacturer's name mentioned are for informational purposes only and do not indicate preference, approval, or endorsements. References to AASHTO and ASTM standards in this presentation refer to private voluntary standards. Compliance with them is not required under federal law. We do have for you a slide with acronyms and abbreviations that will be used throughout this presentation. I will pause for a moment to give everyone a chance to review them. Very good. Now, before we get going, let's go over the expected outcomes of today's webinar. We hope by end of this session, you will understand why aging should be included in balanced mix design, recognize how test temperatures affect the BMD test results, learn about different aging protocols for balanced mix design, and consider how climate and traffic vary nationwide and can impact your balanced mix design testing conditions. Now, these key takeaways will obviously help guide today's discussion. And with that, we'll get started. I will now turn it over to Tim Aschenbrenner to kick off the presentation.
Well, thanks, Ellie. Appreciate the introduction and welcome everyone to our webinar, our fourth in the series of five. I'm going to go over the background here to get us kicked off. Mechanical tests for balanced mix design. These tests are related to distresses, starting with rutting tests. To address that rutting test, we commonly see some wheel tracking type tests like the asphalt pavement analyzer or even the Hamburg wheel track tests. Monotonic tests we're seeing implemented around the country can be the ideal RT or even the high temperature IDT. Those tests are identified to minimize the chance of rutting in your pavement. Cracking tests, I probably need to start off with the types of distresses. There's load and non-load related distresses. Load-related distresses can relate to fatigue, the top-down or bottom-up fatigue type cracking. Non-load related distresses are often environmentally induced, like thermal cracking, or you get some excessive aging like block cracking. And those cracking tests we're commonly seeing implemented around the country are things like the ideal CT, the ideal cracking tests. And then there's others like the Illinois Flexibility Index test, the semicircular bend. And if you get into the non-load related tests like thermal cracking, we're seeing the disc-shaped compact tension. So a lot of choices there to make sure you pick the type of test that most meets the distress you're looking at. Moisture damage, most commonly there is the AASHTO T283 that is commonly called the modified Lotman test, or even some are using the Hamburg wheel track test to help predict moisture damage. Frictional characteristics, those types of tests are starting to be implemented by some states as a part of their balanced mix design. Durability tests like the Cantabro and many others. So a lot of tests, but really you want to focus on the type of distress you're trying to minimize. The A great resource for information is NAPA's Balanced Mix Design Resource Guide. This is always up to date every quarter, and CAT goes through and updates information from each state, so it stays current and is valuable. And on the left-hand side, you can see the map of the different types of tests that states are electing to adopt. Most commonly is the Hamburg wheel track test. There's probably 22 states that are looking at the Hamburg in terms of a rutting test. And then on the right side, you see the list of tests that are used for cracking. And most commonly there, we're seeing states select the ideal CT. I think there's about 22 states that are looking at the ideal CT as their cracking test. Uh, so what's different about balanced mix design compared to the typical volumetric type testing? Well, one thing that we want to emphasize today is that these mechanical tests used in balanced mix design are more sensitive than your volumetric tests or your specific gravity tests. Now we know, for example, the GMB, you're weighing the compacted specimen in air and water. There's some variability there, but these mechanical tests are much more variable. Not only are they more variable, but they're more sensitive to various conditions. And we covered that in the previous webinar in terms of the time in the oven, the temperature of the oven, uh, the amount of heat that these samples and specimens are exposed to can have a big impact in the ultimate test result. Well, in addition to the fabrication having an impact on test results, test conditions also can have a significant impact on the test result. So test conditions, which is today's webinar, what do I mean by test conditions? So generally, we put the test conditions into three bins. There's the loading conditions, the mixture aging conditions, and the testing temperature. Now, loading conditions, they're specified in the test procedure, and what we typically see is most states are following the loading conditions as indicated in the test procedure, which is a good idea. The loading rate Sometimes it's 0.2 of an inch per minute, sometimes it's 2 inches per minute. Whatever that test procedure calls for is an example of the loading rate. Those are monotonically loaded specimens. There's also frequency and amplitude in cyclic tests. For example, the stress sweep rutting, for example, it has certain frequency in the number of cycles per second and amplitude. These repeated load tests, although they can be more appropriately related to performance, they're also more variable and they often take more time. And so we're seeing states find that the monotonic samples seem to meet the needs that they have, but also, well, they meet the needs that the states have in terms of production rate and also accuracy. But we're not seeing a lot of changes of loading conditions compared to what the test procedure calls for. But in this webinar, we're going to mainly focus on the aging and the test temperature. We'll have a lot of examples of aging, whether you're looking at the loose mixture aging or compacted specimen aging. There's short-term and long-term aging. Even the new long-term aging procedure has a lot of options and includes options for both the loose mixture and compacted specimen. And the amount of aging will impact those test results greatly, so we need to use care in terms of selecting the appropriate aging conditions. And then there's test temperature. So we have that compacted specimen, and we're going to run a test. It could be a rutting test. It could be a cracking test. And the test temperature that you run that test at will have a big impact on the test results that you end up receiving. So test temperature and aging, we're seeing states make selections on those very carefully to ensure that they match the performance in the field. So we encourage everyone to reflect. How is this mixture going to be used? Because how the mixture is used is going to have a big impact on that aging time and temperature and that test temperature that you select. There's various mix types and properties. Is it a surface mix? That's going to get a lot more aging. That's where the aging occurs, as opposed to a base mix. The climate, in the graphic, you can see we have different climates around the country, from wet freeze all the way to desert areas. I'm from Colorado, and we'll have some of those areas. We'll have all of those areas in our state. We'll have contiguous roads at 10,000 feet that we have to pave, but then we have high desert areas, and that climate can make a big difference in the aging procedure selected as well as the test temperature selected. So a lot of factors within a state and certainly nationally, and that's why there's no national BMD criteria, because everybody's trying to pick the best mechanical test and the best test conditions with that mechanical test for their application in their state. So as we review the 8 tasks for BMD implementation, today's webinar, we're focusing there on task 3. Task 3 identifies the test to meet the distresses you're looking to minimize, how to run that test. In other words, what are the aging and test conditions that you want to select, and then most importantly, tying those to validating the test to known field performance. And that'll be the key, is selecting aging and test temperatures such that you can get as accurate a validation as possible. And so with that, I'm going to turn it over to Derek for the second section here on aging.
Thanks, Tim. And greetings, everyone. Hope everyone is doing well today. And thank you for joining us for another one of our BMD sessions here. So Tim gave us a really good introduction as to why we're here kind of talking about this topic. What is important about the concept of test conditions? And again, it's at that idea that we're running a given test, right? But there are some things that we can adjust about that test to make it match how we're going to use it. And likely the two big things that agencies look at changing are test temperature, and the aging of the specimen itself. Those are the big ones that they're often looking at, not looking at loading conditions or changing that kind of specifics of the test, but looking at these more often. So we'll talk about the first one here being the topic of aging. So again, you kind of nitpick a little bit and say, well, it's not really necessarily the test condition, but it's the condition of what I'm testing, of the specimen, the mix, whatever it is, and how it's been conditioned prior to the testing itself. So we'll start with kind of a question that I think others have asked, and why does aging matter? Why does this matter? Why do I have to do this? Aging takes added time, it takes added resources. So that's often a very good question to start. And this is actually some information I took from a recent document that's published by the Balanced Mix Design Implementation Working Group that's trying to answer this very question. Why does aging matter in the context of balanced mix design? Well, number one, it's primarily an issue for any of our durability type parameters, or primarily for cracking. And if we just kind of think back to, our entry-level schooling, wherever you got your entry-level schooling when it came to asphalt mixtures, it's that, we need flexibility for this asphalt mixture to retain its resistance against cracking. And we're not worried about that on day one. We're hopefully not, all right? But we have a product, we have an asphalt mixture that when exposed to the elements, it weathers, it oxidizes, it embrittles, right, over time. And that not only with repeated loads or repeated, exposure to the environment and thermal stresses, the material itself is embrittling, therefore making it more susceptible to cracking in general. Okay, obviously it gets more specific with that when we talk about specific cracking types, top down, bottom up, right, thermal, etc. But to generalize, that embrittlement will make a big deal for how it resists cracking into the future, when that cracking really becomes a concern, however long into the future that is. Hopefully it's 7, 10 years, maybe it's 3, okay? But the concept here is that we're testing for a distress. And the idea is that the material that we're testing, well, that's not the material that's really going to crack, or shouldn't. It's the material that's aged off into the future. And so that's where the concept of the aging of this material comes in. And so, the very simple answer to the question, why does aging matter? Number one, because that's when it's going to crack after being aged, and that multiple studies, multiple work has shown that some of these balanced mix design cracking tests show stronger correlations when compared to field performance when it's done with long-term aging. So this is a sampling of data from NCAT and MinRoad, and these aren't the only studies that are out there, but this is just an example that's been pulled together for this publication, when they looked at kind of top-down cracking and thermal cracking on their loading facilities, right, on test track and other test sites. And you see a number of cracking tests, durability-related parameters, whatever you want to call it. And this is just a simple measure of the correlation in R-squared of a relationship between that parameter, right, and the field observed cracking in each one of these categories with and without long-term aging. Now, in this case, it was method E, okay? It's sometimes referred to as critical aging. That's at 135C for either 6 or 8 hours, depending on where you are. Again, the method itself doesn't necessarily matter, but you see that in a number of cases, right, the R-squared, the relationship improved, arguing that there's something missing from testing it in its reheated condition. And again, it kind of speaks back to that logical argument that what you're kind of saying by testing reheated materials is that there's no real significant difference in how your materials age, that I can adequately predict how it's going to, how the embrittlement, how stiff it's going to be in the future by where it is in its reheated condition. And some of the data has shown that's not necessarily true. There are materials that are more aging stable than others, right? Others that might deteriorate more quickly over time, etc. So that is the concept that aging is trying to capture. So here's some other data that the Mobile Asphalt Technology Center through Federal Highway has captured from across the country over recent years. And the MATC has a unique opportunity to test a number of different mixes from across the country. right? And so this is a sampling of some of their samples. Each one of these bar charts represents an individual asphalt mixture sample. And this is where they did CT index, right, in a reheated condition versus some sort of aged condition. On the left, I have method D. So that, if you know the AASHTO standard, that's the 20 hours at the PAV temperature, typically 105, 110, 115 C, right? On the right is reheated versus method E. Again, that's the critical aging procedure 135 C, 6 or 8 hours, okay? So you got comparisons on either end, all right? And what you can see is by sample, what we have plotted is the average CT index in a reheated condition and the age condition in the bar charts. The number on top of them is the ratio, if you will, all right? The ratio of the age condition over the reheated condition. All right, so you're going to see a reduction, right? So in this case, for the first bar, this is 46, all right? So it's about, more than half reduction from reheated. So what you can see here is that from all these different samples from all over the country, taken from the last couple of years, you're seeing that the effect of the aging that's simulated, right, by one of these methods, method D, method E, we'll go through those in a moment, is not uniform, right? It's not a across the board 50% reduction every time, right? Now we're generally seeing them in that area of somewhere to a 40 to a 60%, somewhere in that range, it seems like. There might be a little bit more with method D than method E in cases, but it's non-uniform. All right, it's not consistent all the way across, meaning that assumption of that loss or that effective aging being uniform across mixes isn't showing up in this data. I'm not saying that anyone is necessarily arguing that point, right? But that's the importance of including aging in your balanced mix design framework in some way. So again, you're seeing a lot of variability, some where we saw very little reduction, others where we saw significant reduction. So, again, examples where we see a small amount. And there's differences between the aging methods, but these are comparisons with the same aging method, different materials. So you can imagine that rankings, if you will, comparisons to performance, it paints a very different picture, reheated versus some sort of aged condition. This is an example of similar type data. Again, a different source. This is from some of the work by our moderator, Dr. Ali Haj, with some of the surface mixes on a study they did with surface mixes in Virginia. So in this case, what they looked at was multiple mixtures across the state. So again, this is a little bit more local than that MATC data. This is just mixes in Virginia, but again, within a given agency. And what they looked at was lab-produced mixes, all right? And they did different durations of conditioning or aging. So you have kind of short-term aging, so that's 2 or the 4 hours at compaction temperature. Again, which version of AASHTO R30 is everybody adhering to, right? So you've got the differences between those and the CT index accordingly, all right? Then what they called accelerated long-term aging, right? We got to get our terminology right. What's short term? What's long term? What's medium term? What's in the middle somewhere? But in the end, what's the duration? Here they had 6 hours at the compaction temperature and 8 hours at the compaction. So you're getting 2-hour intervals of this mix staying in that conditioning in for that aging. And what was the CT index at the end? The color coding here, they have a criteria of 70, kind of that criteria there. So that corresponds to that. But same thing that you saw in the last plot. The effective aging is not constant. And again, this may be obvious to many of you that work in this area, but it's an important point to reiterate when we have these kind of conversations about, well, why do I need to do that, right? Well, the data is indicating if we don't incorporate aging, we might be missing something in our analysis. So you see so for example, you're seeing a 50% reduction in that M1, from 164 down to 80. However, it's high above the criteria. All right, M4, you're going from 100 down to 20. All right, you see a large scale decrease right off. So if we go to the next slide, excuse me, this is that same kind of data, right? It's just plotted. right? And you're again seeing that, yes, you could see some general observations and trends, that it's maybe not crazy different. Now, remember, these are all mixes within one state, okay? These are all lab mixes as well, but you're seeing differences in that aging and how it is observed with the BMD results. And I think from a logical standpoint, when we think about it, we have to kind of come to the conclusion in most cases that we would anticipate that an aged material probably more reflective of the real thing than, again, that mix on day one when we're worried about crack. And again, that speaks back to that original why that a lot of the work has shown stronger correlations with actual field sections when we evaluate with an aging. So you want to do an aging condition. You want to consider aging in your cracking evaluation. Again, depending on the type of cracking that you're looking at, that may become more important or maybe slightly less important. What type of mixes are you looking at? Okay. There's a lot of aging methods out there, and this is the current buffet, if you will, of choices, all right, here for long-term conditioning of the asphalt mixtures. Right. Again, this is where definitions are sticky, right? What is long-term aging? How many years does that simulate? The answer is often it depends, right? This is a complex interaction that we're talking about. But this is the selection of items that is currently in AASHTO R121, which is the standard practice for evaluating long-term aging. This is actually, if you look into the history, this was broken out of the other standards in AASHTO to kind of be its own separate thing, to not complicate it with laboratory aging or short-term aging. So you see the choices here. First thing being, what are you going to age? A compacted specimen or an uncompacted specimen, being the mixture itself. In the compacted one, we have this kind of legacy one a little bit, 5 days or 120 hours at 85C. And the work seems to indicate that that will simulate 1 to 3 years. All right. Again, there's ranges in here because aging in Alabama and aging in Alaska are slightly different. Our roadways experience different amount of aging in the field as well. Most are looking at at uncompacted mixtures for aging. Most agencies that we talk to are looking at, conditioning the mix itself rather than doing the specimen. But we'll show examples in a second. Here, the standard has 4 different options, letters B, C, D, and E. All right. B being 5 days or 120 hours at 85C. This is supposed to simulate 7 to 14 years, somewhere in that range. You have method the C, which is a certain number of days at 95C. This is meant to simulate anywhere between 4 and 16 years. This would be, for those that are industry, the result of NCHRP work that basically came up with algorithms and maps that said, based upon your location and how close to the surface, it has a model that tells you how many days you do at 95C, right? But an example would be 3 days, maybe for where I live in Maine. But if you're in, the southern part of the country, it might be a couple of weeks, depending on, am I simulating aging at the surface, etc. But the point is, it's X number of days at 95C. Method D is probably the newest on the block out of all these. Some at the time refer this is to more of like a medium-term aging. This is 20 hours at between 100 and 125C. Right? This is supposed to give somewhere up to 12 years, but again, that's dependent. The temperature here is what changes based upon your location. Right, your location in the country, the more south you are, you condition at a higher temperature than the more north, all right, to try and account for the differences in aging climactically. But the 20 hours is set as more of a practical way to, you have a day's worth of aging, but you don't do the full 24 hours in order to allow some time for preparing specimens, doing your work, etc. And then finally, method E, I mentioned this earlier. This is often referred to as critical aging, often used at the National Center for Asphalt Technology. This is set at 135C, 6 to 8 hours, right? 6 hours for more northern climates, 8 hours for more southern climates. And again, this is based upon 5 to 10 years. Now, we could spend a lot of time getting into the details, all right, that about each one of these, all right? And How many years is it supposed to simulate? There are concepts like cumulative degree days as ways to measure how much aging a general climactic region or something like that will experience. And that's where all of these are developed. So we'll give some examples on the next slide, and we'll have a brief discussion. Well, what makes them different and some considerations that Tim will talk about in the end when you're thinking about what am I going to pick for age, right? This is a table of examples of states and what they have either been using or they're leaning towards in some cases for an aging procedure, right? So you're seeing, number one, a lot of variety, okay? Anywhere from one that is not even listed in Art 121, the state of Illinois that has had BMD implemented for years now. In the lab, you're using 2 hours at 135C for their short-term aging condition. Okay, again, think laboratory-produced material. For long-term aging conditions, they are using compacted specimens at 95C, 72 hours. Again, that's not an option that you saw in the AASHTO R21, all right? But it's being used. There are some other states that are developing some of their procedures that are outside of the options in AASHTO at this time. All right, but you see the others in here. Louisiana is also using compacted specimens. All right. Others are generally looking at D and E. All right. You do have Oregon that's looking at 1 day at 95C, all right, as an option. You see many that are looking at the 20 hours at that, kind of slightly lower temperature, or the 8 to 6 hours at 135. What you're seeing here is a balance between time and temperature. And just in short, the certain things to consider that Tim will go through, there's some practicality concerns here. And also, if you look at the literature, there's often concerns about the impact of high temperatures. The real way to simulate aging is to stick the mix out there for years, right? That's what really happens. Well, we don't have time for that. So we need to accelerate it in some way. So we accelerate it by doing high temperatures, right? That's how we're accelerating in the mixture world. In the binder world, we can do it with pressure. We can't do that with mixtures today. So we're simulating by putting it at a high temperature. And there are concerns that you could go too high of a temperature that's not indicative, that there could be damage to the binder, maybe polymer modified binders. Again, there's been, work out there to draw those concerns that lower temperatures might be more accurate, perhaps. But again, there's a trade-off with time and practicality. And so the real question, I think, would be that, how much aging do you need? And so, again, I'll defer maybe some questions on this to our moderator, Dr. Eli Hosh, but this is some of his work as well, and talked about this before, that how much aging do I need to get far enough from the reheated condition, but also to get so that I don't waste time. I don't want to add extra time into the process. That makes things less practical, less applicable to a quality assurance environment like we're going to talk about in our next webinar. All those kind of concerns. And so they did some work here, taking mixtures and testing them at different aging durations, okay? So you see some results here of kind of the initial, right? No added long-term aging procedure. And again, Ellie can correct me on any of the details later if we have questions, but you're seeing 3 different mixtures here. And no matter whether we're non-reheating or even just reheating, all right, even reheating is imparting a little bit of aging versus non-reheating. And that's been shown many times. There is an impact to reheating, but it's a fact of life for many that it has to be done. But either way, take that as a data point, as your anchor, your first value, right? And then compare it to the multiple days, right? We know that the real aging, down the line, 5 years is a number. But what they did was do this work of the effect of aging over time in kind of creating a curve. And the point that we want to know this, right? We have this answer quickly. We have that number right away. We want to know this. Well, is there a critical time? Is there a time what's just enough aging to be able to predict this well? And what I think you saw in some of the plots and information earlier is that this initial data point, reheated, non-reheated, or design, etc., okay, that it has been shown to not be able to predict the critical field aging time well, that there's significant differences. And if you look at this plot, that kind of makes sense, right? They're not all necessarily, parallel to one another. It's not the same materials. There may be differences there. Again, aging susceptibility, but we don't need to do unnecessarily long aging if it's going to reach a point where it gets steady state and it's kind of constant from this and the rankings no longer change. So you can see in some of this data that at what point was enough aging to get this prediction? And I guess just to think of that as a concept, we don't necessarily have to do aging to a point where it's 15 years old, but we have to do enough to get past maybe the volatility of the data and the unpredictableness of that initial data point to get to a point where it is predictable. So let's just think of that as a concept when considering this. We are never going to fully simulate what happens in the field, right? But we want to try and predict it as accurately as possible. So that's the first kind of big topic, is the concept of aging. Again, primarily in the durability or cracking space, because that's where we worry about those distresses. We worry about them after embrittlement, etc. The other key one that we see that agencies and people are kind of grappling with is the idea of test temperature. And this we actually find largely more on the rutting side. It does apply to all of the testing. It is an important consideration, but we maybe see it a little bit more on the rutting side. So start with a question again. Why does the test temperature matter for BMD? Why does it matter? All right. And the answer really is the testing temperature is important because we want it to be we want to represent how it's going to be used in the field. We want to represent, again, simulate isn't the right word. We're not simulating with BMD tests. In order to simulate the real world, we would have to do, again, repeated load testing. We'd have to do a lot of different things that BMD can't do. It can't be that complicated, right? So these tests aren't necessarily simulating the real world, but we're trying to draw a conclusion, get closer to it. And there could be concerns with testing a mixture out of the temperature range in how it's going to be used, right? And a lot of that concern comes from the asphalt side of it, all right? In this case, we're maybe not as worried about the other components of the mixture, but primarily in asphalt behavior is complex, right? It is temperature and loading dependent, as we all have learned the term viscoelastic properties, etc. That is important. And what comes to mind to me for this is if we think about our own asphalt binder kind of performance grading system. We all know some of the stories about that. I'm sure if you've talked about it before, that if we kind of get to the point and go back in time and we characterize an asphalt test by a penetration at one temperature. And we think and say, well, that one temperature doesn't necessarily predict that asphalt binder's performance at high temperatures, at low temperatures, at all these different frequency and loading rates. That knowing it at that one data point doesn't make you understand the rest of the master curve, if you will, of how that material will perform. Well, that same exact argument lends yourself to this test temperature idea that being able to predict how a material performs at a given temperature is often a fool's errand to try and do not at that temperature, right? Those things are nonlinear. They're nonlinear effects, right? My other example here is going to be on the Hamburg wheel tracker. A lot of our examples are going to be on the Hamburg wheel tracker when it comes to test temperature. My example is that when I was at Maine DOT, we started using the Hamburg wheel tracker to combat some of the durability moisture damage issues that we were dealing with at the time. All right. Now, what we did was we said, let's try out the Hamburg. We got one. And for the most part, we had always heard the Hamburg. Well, people tested at 50 degrees C. So that's what we started doing. Put all our mixes in. We're just going to start messing around with it. Put every main mix in at 50 degrees C. And they all absolutely got destroyed. They absolutely all got destroyed right away. Immediate passes down to failure. All right. And then we did a little bit of digging and said, yeah, this 50 degrees C probably isn't the right thing for our climate. And the fact that we were using minus 28 grades and 64 high temperatures. And, we're on the northern end of the climate in the US and started lowering the test temperature to 45, like some of the other neighboring states had. Okay, had begun evaluation, and things started to match a little bit more. You know, we weren't finding that all our mixes were awful, but that's what the Hamburg was kind of telling us at 50 degrees C, right? Contrast that same 50 degrees C, and we've worked with another state on the other end recently, okay, where they're in the southern part of the US. And they're testing at 50 degrees C, and mixes are coming up great. Even mixes that then failed in the field and rutted in the field. But they had an extremely hot climate, all right? So they were on the other end of it. The point being, this serves as an example that none of these tests are necessarily off the shelf. There are some conditions that you have to calibrate to your own situation. And as Tim said, that is why we don't have national BMD level criteria. So when thinking about this, we kind of put together 3 common strategies with testing and how you can adjust it for your condition. And so one is fixed test temperature variable criteria. All right, so example here would be to maintain a consistent test temperature and then adjust your criteria. So we have examples of this in the next slide. I would say that most would be taking this approach with something like Ideal CT. You have different mixes. You're going to all test at 25C, but you're going to adjust the criteria based upon the type of mix, maybe the binder PG, traffic level, etc. Right? Approach, to the second approach here would be to fix the criteria and vary the test temperature. We often see this more with the Hamburg wheel tracker in a number of states, where their criteria is constant, but they adjust the test temperature either based upon the binder PG or other items or traffic level potentially getting in there, but primarily the stiffness of the mixture, hence the binder PG. Or a third approach that you adjust both of them. All right, then I'm going to adjust test temperature and the criteria. And largely you would do the test temperature again based upon the binder PG, and then adjust the criteria, maybe on the PG a little bit, polymer modification or something along those lines, but then mix type, all right, traffic level, etc. Okay, so let's see some examples of what does this actually look like. And again, my examples are going to be on the Hamburg wheel tracker. And just a reminder, right? Just a reminder that the Hamburg wheel tracker, the very short version, was developed, all right, for the city of Hamburg. Right? I'm trying to shut my Teams up so it'll stop dinging and bothering me in the middle of this. But the test itself was developed for a condition, all right, here in Germany, all right, and look at where that is geographically to, say, Arizona. I always joke about Arizona, Phoenix, Arizona. It might as well be the surface of Mars, okay, as compared to where I live in Maine. It was also done versus a incredibly heavy port and roadways that have very high traffic. That's what it was developed for, 50 degrees C and the criteria associated with it. All right, so keep that in mind before just copying those requirements over to you, over to me in the state of Maine with less traffic, for example. So these are tables that come out of AASHTO MP46. All right, that show the AASHTO, the Hamburg wheel tracking test temperature and criteria by state. And so has this kind of divided, so just have some examples that you can look at. So for approach 1, for the first approach, where we're going to keep the criteria, we're going to kind of look at one test temperature and then adjust criteria accordingly. So we have some examples, all right? Have some examples, say, from Illinois, all right? Illinois is testing all at the same temperature, all right? But they're looking at different pass count depending on the PG grade. With higher PG grade, stiffer binder, expecting to do better, okay? That's an example. Texas is another example, same approach. It's all tested at 50 degrees C, and the number of passes get adjusted. For approach 2, same table. But again, we have some different examples, all right, that will highlight, Colorado uses a maximum rut depth at 10,000 passes, but they adjust the test temperature. And I'll show that development in the slide in a moment. Maine has different test temperatures based upon PG grade, the same criteria in the Hamburg wheel tracker. Same thing for the state of Montana, etc. They are adjusting versus the PG grade. All right, again, to try and incorporate that stiffness part of the binder. Approach 3 is doing both. They both change in some way, shape, or form. Okay, and we have a couple examples of that. California has the Hamburg. They have different passes to failure and different temperatures. All right, Iowa has it based upon traffic, but again has different temperatures based upon the binder. Just an example of them tailoring it to their own situation. And so I thought it was also good, knowing Mr. Aschenbrenner is on the webinar as well, to highlight some of the work that was done in Colorado, that when they looked at the Hamburg wheel tracker, as Tim alluded to, Colorado is an excellent example of a state that has vastly different climatic conditions all within its borders, right? Maybe if you're the state of Connecticut, you don't have this problem, right? But Colorado certainly does, where at the time they had viscosity graded binders, all right? And so if you look at LTPP, high temperature PG, and what those different areas were giving you, they have a lot of different range in the binders that they use. So they felt, and what the work showed, that it wasn't right for them to test it all at one temperature, that they needed to adjust because some temperatures were way too hot for the stiffness of the binder, that they weren't going to learn anything about the mix because at a certain point, the binder is either way too stiff or not stiff enough to give you any valuable information for the test. So that's where they developed this relationship between the test temperature and the high temperature PG. And said, we want to test at a somewhat indicative condition of what it's actually going to see in the field, because otherwise, are we really learning anything? All right. And another example is more of a recent example is work that's been done for the FAA to develop their rutting approach to balanced mix design. And this is what has been developed as something that's an example of that kind of tier 3, or excuse me, that approach 3. Because that was a Freudian slip there. Approach 3, that based upon location and the traffic load, they will have a specification. This is just showing the test temperature end of it, okay? But they're doing the PG high 50% reliability and then relating that to a test temperature. So you're seeing anywhere between 40 degrees for San Francisco, California, up to a high of 64 for Phoenix, for Tampa, etc. Okay, and that also is going to get applied based upon the loading of the type of aircraft that's in that facility, right? To take into account, again, the different stiffnesses, if you will, of the mixture. And this is just an example for Hamburg wheel tracker and rutting test, but you could apply this to any of the others as well. So some tips from those that have worked in this area that we've kind of collected over time. For states that are looking at this, you're concerned about the testing conditions and some of that. Consider using a wide range of mixtures for your benchmarking efforts, all right? From my low stiffness, high stiffness, different PG grades. That's certainly been part of kind of the world out there to consider as well. Consider testing mixtures at multiple temperatures and aging conditions, all right? So don't just start by doing just reheated, all right? Or just one temperature. I picked 50 because that's what it says. All right, that's what it says. That's why I see everyone talking about, I'll just do 50. Consider your condition, especially if you're on the extreme of the country in one way, all right? Your Maines, your, I don't know, New Mexico, Florida, Washington State, whatever it is, all right? This is especially important for any validation efforts that you're doing. If you're going to rely on something for validation, it's worth the extra testing to try a couple aging methods. Because you may not know which is the best aging method, but might as well test it at that point, and that will prove out. If you have data for a validation site and you have it at different aging procedures, well, that data will show you which one was more indicative. Maybe the reheating is just as indicative as your aged, but you'll have the data to make that decision. Oh, you can also follow a process, all right, in order to determine proper testing temperatures. And this is a kind of schematic or plan, if you will, that many have used for the Hamburg. And if they have kind of good and poor mixes to calibrate this against, they will test it at multiple test temperatures. This is what was done in Colorado. Maine did a similar thing. Take the same mixture and test it at 1 degree increments, right? When a good mix then you lower the test temperature until it starts to pass, whatever your criteria is. If you're looking to just adjust temperature, If you're looking to do criteria, then you could adjust that as well. Find poor mixes, go the other way. All right. So I take my example when I was in Maine, we had some mixes that passed. They were using a polymer modified binder. It passed at a lower temperature, still failed in the field. And that was what sold us on having the increased test temperature with higher PGs, that it was missing something. So this is something that you can iteratively get at the result that you want. So these are some tips on how you might do some of your initial testing to maybe calibrate or give yourself the data to figure out what the conditions are that work for you. And so with that, I'm going to give it over to Tim to summarize a bit of what we've learned and challenges and what some effective practices that all of you can consider as you continue your balanced mix design journey.
All right, well, thank you, Derek. Yeah, I'm going to do some summarization here of the challenges and highlight some effective practices of dealing with these testing conditions, particularly of aging and test temperature. And a lot of it goes to validation. As Derek mentioned, we need to select this aging protocols and test temperature based on validation. And there's a couple things going on with validation. The primary goal is to make sure the mechanical tests relate to the field performance. So if you're looking at a certain type of distress, does this test and the test result relate to that type of distress? In this case, if you're looking to use this particular test for thermal cracking, you're probably not going to reduce the amount of thermal cracking in your state. However, if you use this test for top-down or bottom-up fatigue type cracking, you can probably make improvements in pavement performance. So first of all, we want to pick a test that relates to the type of distress. And then secondly, we have to pick the appropriate criteria. What's the threshold? And as Derek went through the data, we saw that aging is going to impact those test results, and the test conditions, or that test temperature, is going to impact test results. And as a result, that will impact your criteria. So really, to set responsible and defendable specification thresholds, we need to consider aging and test temperature as part of that process. So for validation, as an example, we have a couple of tasks. That first task relates to the test relating to the type of distress. Does the test matter for performance? And this data shown here, this data is from the ALF, the Accelerated Load Facility, that's at our Turner Fairbank Highway Research Center. And the actual CT index from those test sections to the amount of cracking on those test sections are shown. It's accelerated load facility, so it was in place only for a relatively short period of time, not many years, only many months. But generally, we see a good correlation with the higher CT indexes giving high cracking resistance and the lower CT indexes giving low cracking resistance. Now, one point here to emphasize, the balanced mix design is not going to cure everything. In this particular case, this section was next to the edge of this site, and there are some drainage concerns. And so we seem to get a very good test result, but moderate to poor performance. It wasn't because of the mix, it was because of the drainage situation and the base. So as a result, balanced mix design will not cure everything. We still need to have good bases. We have to have good drainage. You have to use tack coat, or else we could be wasting a lot of money on balanced mix design. And the second factor here to look at is what level of performance do I expect? So if I'm, say, on an interstate or one of my high investment projects in my agency, I might be looking at a CT index of 100 or 120. But there's other parts of my state, other parts of my agency, maybe farm to market type roads, low volume roads, where I just want to avoid these low cracking resistant mixes. So maybe I might want to set a CT index of 60 in those cases. So knowing the type of performance you expect is a good thing you can get out of a good validation study. Now remember, the tests that you're running will be impacted by the aging and test temperature. and that will impact your comparison to your validation results as shown here. So you have to keep in mind this was an ALF that was only out there for many months, not many years, and that also will then have an impact in setting criteria. So some considerations when going through this process. What do you want to ask? What do you want to consider about aging and test temperatures? So consider the level of aging for your situation. Targeting distresses, cracking obviously is more of a long-term distress. We need long-term aging. But like Derek said, there's longer long-term aging and there's intermediate or critical long-term aging. What might fit best for the types of mixes and overlays you're doing? Rutting, on the other hand, that often occurs in the near term. Short-term aging is probably more appropriate for that. Climate will have a big impact. If you have areas in your state that have very high temperatures, like in Colorado or southeast high desert areas, versus the Rocky Mountains where you have the roads at 10,000 feet. Arizona could be another example. They go snow skiing in the winter in the northern part of their state, and in the southern part of the state, it is very, very, very hot. And the climate that you have in your state is going to impact aging. There may be more than one type of long-term aging you want to consider. And then also the type of mix. Clearly the aging impacts those surface mixes the most, but those surface mixes act as a insulator or a barrier, and the base mixes don't age quite as much. So these are things you should ask yourself and consider when setting up aging. Now, in doing this, we don't want to over-engineer the situation. We want to consider some practical impacts in terms of balancing time and temperature. So for time, when you select a procedure, consider, well, what time does your lab open in the morning? What time do the technicians arrive? What time does your lab close in the evening? What time do technicians leave? Because you're going to have to pick a time for that long-term aging that you're going to actually have to do in the lab. And you want to be mindful of some of these practical considerations. And when you select long-term aging, how many temperatures are you going to select? And that might depend on how many ovens you have, how large are the ovens. If you pick multiple temperatures, then you're probably going to need multiple ovens. Certainly want to be accurate as engineers, but we also want to be practical to be able to get these mixes tested. Now, the lab operations related to quality assurance, keeping in mind quality assurance is all of those planned and systematic activities to improve quality. It would include mixed design approval, mixed design verification, and even acceptance. The aging time could vary based on those applications. If you're just going to do it for mixed design approval or verification, that's one factor. But when you go to the field, of course, everybody wants results quickly. You're at a plant, you don't have a central lab with a lot of ovens, you have maybe a trailer. Things are going to be very different for acceptance. So when you're looking at aging, consider all aspects of your quality assurance program. And another consideration is the future. You have mixes that you're used to seeing now, but as we know, things are going to change. There could be more additives. There could be more use of warm mix asphalt. There could be more use of recycling agents. So things you're doing today may not be what you're doing in the future. And some of these things, like warm mix asphalt and recycling agents and others, can be impacted greatly with the amount of long-term aging that's done. So the future needs to be a consideration. Now, test temperature considerations. Consider the test temperature for your situation. As Derek mentioned, mainly with rutting, but it could also be a factor with cracking as well. But that's impacted by climate and the binder grade. I remember in Colorado with LTPP, we came up with the need for 10 or even 12 PG grades if we followed LTPP by the book. But practically, the binder suppliers would not be able to provide us that many. So we had to do some similarization, and we boiled it down to 4 PG grades that we thought would work adequately around this state. And again, targeting distresses. Derek highlighted many examples where that rutting example is going to make a big difference. If you're running a rutting test for a project that's being paved at 10,000 feet above sea level, that the high temperature is 70 degrees Fahrenheit for the entire year, and you use that same test temperature for your high desert areas that get it over 100 degrees, the results will not be meaningful. And consider the impacts of using these multiple temperatures. You have to consider the technical accuracy with practicality, because we do need to build these pavements. So some key questions, some takeaways. Your BMD tests, do they properly reflect the conditions? Are there certain distresses you're trying to minimize? Do these tests will these tests do the job to minimize those distresses for you? For aging, are these for aging and test temperatures, are they appropriate for predicting your long-term performance? And the answer to that question will likely fall into validation. So plan to validate. Finally, we don't know the answer up front. It's an evolving process. So if you set some test temperatures, if you set some aging protocols initially, don't be afraid to evolve. Things can change over time as you learn more, and you can update your test procedures and aging protocols accordingly. But not knowing those precisely at the beginning is not necessarily a good reason to avoid implementation. So the critical challenges we discussed, aging, defining the appropriate aging based on your climate, mix type, and distresses. Those test temperatures, making sure things are practical and useful, but then relate to performance, and then validation. Not just validation initially, but ongoing validation as you go through the process. We've seen many states set initial criteria based on test temperatures and aging, and after 2 years, after 4 years, continual evaluation, they're not afraid to make adjustments in their thresholds or their test procedures based on the performance they're observing. So as we wrap up webinar 4 on testing conditions, we did a deep dive on task 3, really going a little deeper into aging and test temperature to show how they can impact your validation and test procedures. Hopefully you have some good tips and tricks to help you with your validation process and your implementation of BMD there. And then highlight our webinar 5 coming up in about 1 month. We'll discuss applying balanced mix design to quality assurance. Just like to highlight our FHWA website. The QR code there can be accessed to get to our BMD website. And then a workshop. We have we believe we have an in-person workshop available. If you're interested, do that QR code and get a hold of us, and we'll try to do our best to get a workshop available for you. So we certainly thank you, appreciate your attention, and I'm going to turn it back to our moderator, Ellie, for any questions that may have popped in.
Thank you, Tim. Thank you, Derek, for shedding light on BMD testing conditions and their impact on test results. We do have few questions. I will start because especially Tim, you talked or re-emphasized at the end on validation aspects. So one of the question came when Derek, you presented that slide 20 on the aging methods, the short-term and the long-term aging methods for the various states. The question was which states performed field validation in determining their results. So if you want a little bit maybe talk about that, that would be great.
Yeah, sure, Ellie. It's an excellent question. So Illinois definitely in there, just looking at the list here, Illinois definitely did aging when comparing the flexibility index results that they got. to the end performance. So I know that was part of their decision to do that long-term aging procedure. That was part of their development. Louisiana, when they looked at their results and they calibrated their criteria, they used that aging condition. And if you ask Louisiana why they still stick with that method, it's an older method. It's been around a little bit longer. Why they don't use one of the new ones? They say, well, because we validated using it, right? And that they validated kind of using that method. The others, I think, Texas that continues to do their work. They're doing their test sections and evaluating it at the aged condition and a reheated condition. So again, they're not relying on that one data point. They're doing an aging condition to compare. So I think those are some of the examples. Virginia, another one where they're doing the aged condition against their field sites where they're going to track performance, among others. So those are the ones that certainly come to mind. And then lastly, Wisconsin, same thing. They have a validation experiment and they did that age condition comparison for that. So I think the vast majority of them, they've included that in whatever their validation effort is.
Excellent. Very good. And a related question to that, whether the equivalence between the various aging methods and the time in service range, whether what based like on binder stiffness, on mixtures, on performance testing.
Yep. So as I understand it, and again, I'll let Ellie and Tim correct me if I'm wrong here. I think most of these methods are done primarily through binder stiffness, not necessarily a CT index in the field after 8 years, because we haven't really reached that yet, right? In a lot of cases, this is primarily based upon those kind of times of how long does this represent. I think primarily is done through extraction of binder from a surface that's 7 years old and then comparing it to an aged version or something along those lines in some of the work that I've seen.
Right. And if I may add, Derek, so
Absolutely, please.
it all started with the NCHRP studies, which is mainly was based on the binder stiffness. But what I've seen that you use that number as a starting point, and then you look at your CT values and how it evolves with the aging, and then you may adjust that relationship between, for example, the 95C and 135C based on the BMD test, or maybe based on a mixture stiffness. So binder stiffness, it seems to be used as a very common as a starting point to see where to target, how many hours, and then you try to bracket that and then validate this with your BMD mechanical test.
Yep.
Excellent.
Yeah,
So
sometimes, Ellie, I might add in terms of implementation, sometimes it's that chicken or the egg approach, and people might say, oh, gee, I don't know the aging, so I can't do balanced mix design. But if I do balance mix design, then I'm not sure what aging to use. And sometimes I think it's good to take the approach of evolution. I think there's a lot of good information in the AASHTO's long-term aging procedure, that AASHTO R121. And as a baseline to get started, I think that information can be used. And it's best to use that as a starting point, but then not be afraid to evolve over time as you there's more research studies out there as you learn more about the situation in your state. But I always hate to hear that, oh, we can't implement balanced mix design because I don't know which one of these aging procedures to use. Evolution is a good thing.
absolutely.
And I'll just add one other kind of caveat. I completely agree with what Tim just said. I think the aging topic, I think we've seen some agencies feel paralyzed in that case, almost like it was with cracking tests 10 years ago that, oh, there's too many choices, and many have kind of settled on the ideal CT. I think sometimes there can be more loss in indecision than wrong decision in this case. And like Tim said, you can still get started. You don't need to have a perfect BMD spec to get started. There will be an iteration of this over time, but it is an important consideration to kind of think about up front.
Right. And there's a related question to that on slide 17, when you, Derek, presented the Virginia data. So it appears that the aging temperature is a compaction temperature in this case, which doesn't align with the R121. Is there a specific reason for that?
Yeah, I think that, certainly I think what Ellie and the group and again, Ellie, please correct me if I'm wrong, but I think you're looking ways to age it, but also be practical, right? In the idea that you're already going to put it at compaction temperature. Can you just keep it at compaction temperature for a certain period of time to aid in the practicality of it, but still get your kind of necessary thing? And I think that's where you can make adjustments to these procedures to meet you, knowing that what is the intent of it. And so that's what some of what Tim talked about at the end is to consider the practicality of this, because, if it doesn't work for you, you're not going to do it at all. So how can you make it work and still get enough aging to increase the reliability of your prediction of performance?
Very good. So to just to reemphasize this, because Virginia uses the compaction temperatures for short-term aging, and then obviously to minimize the use of additional ovens at different temperatures, they opted to continue the same temperatures for long-term oven aging. So that goes back to just exactly what you mentioned, Derek, that, practicalities, what Tim, kind of summarized at the end, how many ovens do you need to allocate, right, during whether your mix design or your productions versus if you can get away with a single oven at the same temperature. So those might sound a little bit sometimes, obvious, but sometimes we might overlook them, when we are looking at trying to, as much as possible, to predict the appropriate aging in the field, when sometimes you may gonna have to be a little bit more flexible to be more practical. Another question is related here to the really the differences between, I think it's more related to the differences between lab produced mixtures and cores. So the question was about, is it common to see differences, for example, the APA test results between lab mix samples and field core samples, even when the mix design itself meets the specification? And I believe that question can apply also to any BMD test, not necessarily only the APA.
Yeah, so I see the question, and I'll say, is that I think the question says, is it normal? I'm not. Is it unusual? No. It's certainly, we see that there is, when we talked about specimen fabrication in our last webinar, a challenge to BMD is that often many are finding that I run it in the lab and I run it in the field and they give you different answers, whether that's a field core or it's plant produced mix, right? And again, we could list the number of ways that mixing in a lab and mixing through the plant are different. There's every different way, right? It's the best tool we have to approximate what we truly do, but it's never really going to get there as far as what you truly make. So I guess that's where we've talked about the importance of including plant-produced mixtures somewhere in your mix design process, because that's the true product, right? That's what's really going out on the road. So consider those differences, try and make them different. The one other thing I'll give with field cores is field cores then add a whole level of complexity, right? They're not at the prescribed air voids. So now we're comparing not just apples and oranges, we're comparing apples, oranges, and a Toyota Camry. Or some, they are significantly different things. So need to acknowledge that why the cores might fail and the others might do well, but they're still valuable information, but knowing that they are not the same thing when you're comparing against one another.
Yeah, and very good. And I might just add to that, as you go through and set up your validation sections, this is very important consideration. So as Derek mentioned, we have the lab mixed and plant mixed. He already mentioned that they're very different. Certainly we recommend sticking with the plant mixed, but then when you have lab compacted and field compacted, they can be very different also. So when you set up your validation sections, start with the end in mind. What are you going to want to do for your mix design? What are you going to want to do for acceptance? And then make sure you're gathering that data as you set up your validation sections to use the appropriate plant mixed and lab compacted, or whatever strategy you have. Because then in hindsight, as this question alludes to, in hindsight, well, I didn't like how the original validations was set up with lab compacted, so now I want to see what field compacted does. Well, then wrench is now thrown into the cogs unless you set that up initially. And I can say from my experience, just with the Hamburg, we did plant mix lab compacted, but then we started getting cores, and we did see very commonly a big difference between lab compacted and field compacted results. But our validation was set up on lab compacted, so that was the lab compacted was the gold standard by which we applied specifications.
And not to complicate things, just to add to that, from a recent experience, the lab mix design on one of the projects turned out to be with past the criteria and everything, but when we went to the collected core or even the reheated plant produced materials, actually did not pass the criteria. What turned out to be that the binder source changed. So that's also something to keep in mind as you go from the lab to the full production. There might be some changes along the way, whether for the good or for the opposite, but there may be some changes that, you need to take a closer look at that. So another questions here is related to the slide, I believe, with the when talking about the different criteria and the testing temperatures. Since having a national standards on this, from a state highway perspective, it may not be practical given the differences, the resources that the states have. How does FAA approaching that from a national perspective when it comes to the BMD testing?
So, Ellie, and I saw John ask the question. I think when you think about it, right, and Ellie, please, add as well, that what you see them doing is not trying to take a test temperature and a number that applies to the entire country. And I think that's what we're talking about when we say there is no national criteria, right? When you do think about FAA, their application of their mix is a relatively small window as compared to maybe DOTs, right? Some DOTs that own every single roadway in the state, they have a wider range between their local roads and their interstates. FAA is still concerned with, right, your runways, all those applications certainly, but at least they have a somewhat narrow focus on the type of mixtures they have. And what they are doing is altering their test conditions to account for the use of the mix and the climate of the mix. So I think that's where they're able to do that in their way, right? You still have the concern about, well, are the distresses the same in an airport here versus there? And that's where maybe different tests might come in for different states. But I think that they are kind of trying to achieve that by altering the test conditions to the place that they're using the mixture. And Ellie, please, add whatever I missed.
No, you got it. I think you got it, Derek. If you think about it, just to reiterate this, the P401 mix is the P401 mix, right? Regardless where it's going to go, or the P403. Whereas this is not the case in the state highways. Every agency had their own specification and so forth. So the way FAA is approaching is we want the test to be representative of the geographical location where that mix is going to go, and then the traffic that it's going to be subjected to. And that's how the testing conditions and the aging conditions and the test criteria are actually being recommended for the FAA BMD testing.
And I guess I would just add, not necessarily to the question, but just in terms of implementation, I think this work was fantastic. It's very phenomenal work, and I think it gives a lot of good insights for states around the country that may want to use the Hamburg. But the thing I would think is worth repeating is that PG high temperature at 50% reliability. Like normally we think of our PG grades, the high temperature is at that 90 plus reliability. It's like a PG 58 or PG 64 is at that 90 plus reliability, but these are at 50% reliability. And so that's just an important thing that's worth mentioning. But if you have that in mind, I think this could give you excellent starting points for using the Hamburg for a rutting test.
Very good. Thank you, Tim. We do have a follow-up question. As part of the validation, whether anyone is using, any of the states are using or creating like an aging, quote unquote, master curve for their state, similar to what we use in the binder, so that they can apply a correction or adjustments to accelerate field acceptance test.
Yeah, Ellie, and the question, I think there are efforts by agencies to somehow account for aging without having to actually do the aging, right? There's an NCHRP project. I believe its title is Incorporating Aging into Quality Assurance for Balanced Mixed Design. And really the tenet of that project is that you may not have time to do the aging under quality assurance. Is there some sort of framework to incorporate aging by some scaling factor or something? The what hasn't been determined from that project, but the problem is certainly what you're getting at there. I think Louisiana is another state that is looking at, their aging procedure, when you look at it, is very time conducive, takes a lot of time. So they can't do that, and that's a barrier for them to do what they currently do in mixed design into quality assurance, into the quality assurance environment. So they're looking at, scaling factors, something like that, that might allow them to bring that aging part into acceptance and quality control in some way. I don't think it's taking the form of some sort of master curve analysis or modeling, but there are efforts to incorporating aging somehow into that without having to do it all the time, if that makes sense.
Yeah, and I might just add on to that from an implementation perspective. I think we talked a little bit about the balance of accuracy versus practicality. And doing a research project like that's going to be very complex. And then when it comes time to implement, it will be very complex with maybe a lot of ovens and a lot of temperatures, but always practicality has its benefits, especially in the types of work we're doing. Sometimes the practical answer may not be perfect, but it's close enough to give us a lot better mix than we have today.
Very good. I don't see any other questions in here.
I think I saw one, Ellie, from Delmar about the tier 1, 2, 3.
All right, I may have missed that. Okay, yes. So, yeah, this is a question, Derek, about the different tiers for the upcoming balanced mixed design framework, suggesting 3 different tiers. And how does this whole thing relate to the BMD framework?
Yeah. I think that it relates in the fact that it's not necessarily tied to tier 1 is this and tier 2 is this. No matter what you're doing, the test and the proposed new AASHTO standard, which is what is being discussed here right now, is that a framework for a revised, framework of balanced mixed design is being proposed to AASHTO right now. And it's proposing to move away from the current approach ABCD to tiers and rethink that. I don't think it's necessarily significantly affected because the whole standard rests on the fact that you're going to do mechanical testing, mechanical balanced mixed design testing at conditions that are indicative of your situation. And those conditions include aging and test temperature, right? And those are those 2 big variables that we see people adjusting. So what I do believe is that those have got to be, reflective of your situation if you want to have that confidence to move to more reliance on balanced mixed design and higher levels of the tiers. So I think that's necessary, and that all goes back to validation and having confidence in the criteria and the tests that they're going to get you performance. And that comes from having the right test conditions.
Very good. Thank you, Derek. I think that will bring us to the end of our webinar today. So the The recording will be available for the webinar in a few weeks on our website. And then we ask you please to take a few minutes to participate in a brief survey. I'm gonna post that survey again in the chat box, and would like to see you again in about a month on June 3rd to talk about maybe even a more important topic on how to introduce or integrate the balanced mix design into quality assurance. We hope to see you back then, and thank you everyone for attending today. And I want to thank Tim and Derek for doing an excellent job. And please feel free to reach out at any time if you have additional questions that we did not answer in this presentation today or something else related. Just please reach out. Thank you very much.
Thanks,
Thank
everybody.
you very much.
Thank you, everyone. Appreciate it.
Thank you, Ellie. Thank you, Tim.
Thank you.
Thank you, Derek.